Hey there, ready for a deep dive?
Absolutely.
This time we're tackling data structures and algorithms.
The backbone of pretty much everything digital these days.
Yeah, everything from apps to, well,
This very podcast you're listening to.
exactly. But data structures and algorithms, those can sound a bit intimidating.
True, but they're really just clever ways of managing and processing information.
Hmm,
Think of it like this.
okay.
You wouldn't just toss all your tools into one giant box, would you?
Definitely not.
You'd never find anything.
I like my toolbox neat and tidy.
Exactly. Data structures are like specialized toolboxes for your data,
Okay.
each with its own unique way of keeping things organized and easy to access.
So it's about making information easy to find and use.
Precisely. And just like you wouldn't use a hammer to screw in a light bulb, different algorithms are best suited to work with different data structures.
Makes sense. So let's start with data structures.
This is good.
Our source material mentions two main types, system-defined and user-defined.
Right.
What's the difference?
Well, think of system-defined data types as those basic building blocks you get right out of the box.
Okay.
Things like integers, decimals, and characters, the fundamental types provided by programming languages themselves.
Got it.
But the real fun begins with user-defined types.
Ooh.
These are the custom structures we create by combining those basic building blocks in clever ways.
So, like using bricks and cement to build a house, you're saying?
Exactly. We take those simple elements and create complex structures tailored to specific needs.
So a music playlist could be considered a user-defined type.
Absolutely.
It's built from individual song files, the system-defined building blocks,
Right.
but organized in a specific way.
Yes, in a way that makes sense for listening.
That's a really clear way to visualize it.
Good.
So we've got these building blocks and custom structures, but how do we measure how efficient our algorithms are at handling all this data? The source mentions something called Big O notation,
Yes, big O notation.
which sounds a bit intimidating.
It's not as scary as it sounds. It's just a way to express how the performance of an algorithm scales with the size of the input data.
Okay.
Imagine you have two libraries, one super organized and one completely chaotic.
I can picture that.
Finding a specific book in the organized library will be much faster,
Right.
especially as the number of books increases.
For sure.
Big O helps us quantify those differences in efficiency.
So Big O notation tells us how well an algorithm can handle a growing amount of data.
Exactly. For example, a linear search algorithm where you check each item one by one would be denoted as ON.
Oh,
This means the time it takes to search grows linearly with the number of items.
makes sense.
But a binary search, which takes advantage of sorted data by repeatedly dividing the search space in half,
Okay.
is OLOGN.
Oh,
This means the time grows much slower, making it far more efficient for large data sets.
wow. So it's like comparing a snail crawling through each item to a cheetah strategically jumping towards its target.
That's a great analogy.
Now let's get into some of those common data structures.
Sure.
Our source mentions stacks, queues, linked lists.
Right.
It's a whole zoo of organizational strategies.
It is quite a variety.
Let's start with stacks.
Okay.
What's the best way to visualize those?
Stacks are pretty simple to grasp.
Good.
Imagine a stack of plates.
Okay.
You can only add or remove plates from the top. Right.
Right.
That's the defining feature of a stack, last in, first out, or LIFO.
Lifer.
The last plate you add is the first one you take off.
Okay, I can picture that.
Good.
But why would we want to organize data in such a way? What's the practical use of this last in, first out approach?
Well, stacks are incredibly useful for tracking a sequence of actions or operations.
Okay.
Think about the undo function in your favorite software.
Okay.
Each action you take gets pushed onto a stack.
Mm-hmm.
When you hit undo, it pops the last action off the stack, reversing it.
I see.
Function calls in programming work similarly, keeping track of which function called which to ensure everything executes in the right order.
So it's like a trail of breadcrumbs, but for data.
You could say that.
All right, next up, queues.
Okay.
I'm guessing we're talking about waiting lines here.
You got it.
First come, first served.
Exactly. Queues are all about first in, first out, or FIFO.
FIFO.
Just like a line at the grocery store, the first person in line is the first one served.
Makes sense.
This makes queues perfect for managing tasks in a specific order.
So anything that involves processing items in the order they arrive would use a queue.
Exactly. Think about a print queue.
Okay.
You might send multiple documents to the printer,
Right.
and they'll be printed in the order they were received,
Got it.
or task scheduling in an operating system.
Uh,
Tasks are added to a queue and processed one by one in the order they were added.
These analogies are really helping me understand how these data structures work.
Good. I'm glad to hear that.
So far, we've got stacks for tracking actions and queues for processing things in order.
Right.
What about linked lists?
Ah, linked lists.
What should I picture for those?
Imagine a chain of paper clips.
Okay.
Each paperclip holds some data and a link to the next paperclip in the chain.
Like they're all connected.
Exactly. Unlike arrays where data is stored contiguously in memory, linked lists can easily accommodate insertions and deletions.
Oh, okay.
You can just unlink a paperclip to remove it or add a new one anywhere in the chain.
So linked lists are great for situations where you need flexibility in adding or removing data.
Precisely.
Like playlists.
Exactly. They're perfect for things like playlists where you might want to rearrange songs, add new ones, or remove ones you're tired of hearing.
Or a photo album.
Yes. You can easily insert new pictures or remove old ones without having to reshuffle everything.
All right, I'm starting to see how each data structure has its own unique strengths.
They do.
What's next? Trees?
Yes. Trees are hierarchical structures that branch out, well, like trees.
Makes sense.
They're everywhere, from family trees to file systems on your computer.
Oh, wow. I hadn't thought about it like that.
And one particular type of tree, the binary search tree, is incredibly efficient for searching.
Okay.
By organizing data in a specific way, we can quickly narrow down our search, finding what we need much faster than with linear search methods.
So it's like a choose-your-own-adventure book for data. You follow the branches based on the value you're searching for.
That's a great way to think about it.
You know, it really is amazing how much thought has gone into organizing information effectively.
It is fascinating.
And speaking of clever organization, what about heaps? Those sound intriguing.
Imagine a tournament bracket
Okay.
where the winner is always at the top.
Right.
That's the core idea behind a heap.
So the element with the highest priority is always at the root.
Exactly. This makes heaps perfect for situations where you need to quickly access the most important item.
So it's like a priority list that automatically sorts itself.
You could say that.
Pretty cool. What kind of real-world applications would use heaps?
Well, heaps are used all the time in task scheduling, where the highest priority task is always executed first.
Makes sense.
They're also used in priority queues, where items are dequeued based on their priority rather than their arrival time.
Interesting.
And you'll find heaps used in algorithms that need to quickly find the top K elements in a data set, like the top 10 search results or the top 100 songs on a music chart.
Wow, we've covered a lot of ground in the world of data structures.
We have. It's quite a fascinating field.
But organizing is just the first step, right? We need algorithms to actually do something with that data.
You're absolutely right. Data structures provide the framework, but algorithms are the engine that drives the digital world.
Makes sense.
In the next part, we'll move on to algorithms and explore how these sets of instructions manipulate data in all sorts of fascinating ways.
Can't wait. But for now, let's give our listeners a chance to digest all this incredible information about data structures.
That sounds good.
Until next time, keep those brains buzzing and stay curious.
Stay curious.
Welcome back.
Ready to dive back in.
Absolutely. Last time, we explored that fascinating landscape of data structures.
All those ingenious ways of organizing information.
Right. And today, we're delving into algorithms.
The instruction sets that make our digital world tick.
The engine that makes it all work.
Exactly.
Our source material mentions searching and sorting algorithms as a good starting point.
Yeah, they're fundamental.
I've definitely heard of them, but I'll admit I'm a bit fuzzy on the details.
Well, imagine you're looking for a word in the dictionary.
Okay.
You don't just start at page 1 and flip through every single page, right?
Of course not.
You probably open the dictionary somewhere in the middle and then narrow down your search.
Based on the alphabetical order.
Exactly. That's essentially what a binary search algorithm does.
Interesting.
It leverages sorted data to find what you're looking for super efficiently.
So it's a divide and conquer strategy?
Precisely. Each step eliminates half the possibilities.
Got it.
And when it comes to sorting, algorithms like merge sort employ a similar philosophy. Imagine you're organizing a deck of cards. You might divide the deck into smaller piles, sort those piles individually, and then merge them back together in the correct order.
Makes sense.
It's all about breaking down the problem and tackling it in a systematic way.
So are all sorting algorithms based on this divide and conquer approach?
Not necessarily. Some algorithms, like insertion sort, take a more incremental approach.
Okay.
Imagine you're building a hand of cards in a card game.
Okay, yeah.
You pick up one card at a time and insert it into its correct position within your hand.
Right.
Gradually, you build up a sorted sequence.
That's interesting.
Different sorting algorithms have different strengths and weaknesses.
So how do we know which one's best for a particular task?
That's where big O notation comes in handy again.
Right, big O.
Remember, it helps us compare the efficiency of different algorithms as the amount of data grows.
Yeah.
For instance, merge sort typically outperforms insertion sort for large data sets because its time complexity grows more slowly.
But for smaller data sets, insertion sort might be better.
Exactly. For smaller, nearly sorted data sets, insertion sort can be quite efficient.
It's amazing how different approaches can be better suited for different situations.
That's the beauty of algorithms. There's often more than one way to solve a problem.
And choosing the right algorithm can make a huge difference in terms of performance.
Absolutely.
I'm starting to see how these algorithms are working behind the scenes in so many everyday tasks.
They really are everywhere.
What other algorithmic wonders are in store for us?
Well, our source material mentions something called hashing, which is incredibly clever.
Hashing.
Yeah.
Oh.
Think of a librarian who can instantly point you to the exact shelf and book you need.
Without even searching.
Exactly, without having to search through the entire library.
That sounds almost magical.
It's the power of hashing.
How does it work?
It uses a special function to convert a key, like a book title,
Okay.
into a unique index within a data structure called a hash table.
A hash table.
Right. And this allows for super fast data retrieval, making it ideal for applications like databases and password storage.
So it's like a super efficient lookup system.
Precisely.
But what if two different books have the same title?
Ah, you've hit upon a potential issue known as a collision.
A collision?
Yeah, it's possible for different keys to produce the same hash value,
Oh, I see.
leading to conflicts within the hash table.
So how do you deal with that?
Well, there are clever collision resolution techniques that have been developed.
Okay.
One common approach is separate chaining.
Separate chaining.
Yeah, where each index in the hash table points to a linked list of items that share the same hash value.
So it's like having multiple books with the same title.
Right.
But the librarian has a system for keeping them organized within that shelf.
Exactly. It's all about maintaining order even in the face of potential conflicts.
That's pretty neat. I'm really starting to grasp the power of algorithms.
They are powerful tools.
But we've only scratched the surface, haven't we?
That's right. There's a whole world of algorithms out there.
So what else can these clever instructions do?
Well, beyond searching and sorting, there are powerful algorithm design techniques for tackling more complex problems.
Okay.
Our source material delves into backtracking and dynamic programming.
Backtracking and dynamic programming.
These strategies offer elegant ways to approach problems that might otherwise seem insurmountable.
Backtracking, that involves making a decision and then undoing it if it leads to a dead end.
Exactly.
Like navigating a maze.
That's a great analogy.
You try a path, and if it doesn't work, you go back and try a different one.
Precisely. Backtracking is like systematic trial and error. If a path doesn't lead to the desired outcome, you backtrack to a previous decision point and try a different route.
Makes sense.
It's used in everything from solving Sudoku puzzles to planning delivery routes for packages.
So it's applicable to a wide range of problems.
Absolutely. It's a very versatile technique.
Now, what about dynamic programming? That sounds like it involves computer programming, but I have a feeling it's more than that.
You're right. The name can be a bit misleading.
Okay.
Dynamic programming is actually a technique for optimizing problems.
Optimizing problems?
Yeah, by breaking them down into smaller, overlapping subproblems and storing the solutions.
Storing the solutions.
Right. This avoids redundant calculations and can drastically improve efficiency.
So it's like remembering the answers to a math problem so you don't have to recalculate them every time.
That's a great way to put it. One classic example is calculating the nth Fibonacci number.
Right, the Fibonacci sequence.
The straightforward recursive approach involves a lot of repeated calculations.
Okay.
But with dynamic programming, we store the previously calculated Fibonacci numbers, making the process much faster.
It sounds like dynamic programming is all about finding clever ways to avoid unnecessary work.
It is. It's all about optimization.
What kind of real-world applications benefit from this technique?
Dynamic programming is incredibly versatile. It's used in GPS navigation systems to calculate the shortest route,
Oh, wow.
taking into account traffic conditions and other factors.
That's amazing.
It's also used in financial modeling to predict stock prices.
So it has applications in finance, too.
Absolutely. And it even plays a role in bioinformatics, where it's used to align DNA sequences.
Wow, that's incredible. It seems like algorithms are constantly pushing the boundaries of what's possible.
They really are. It's an exciting field to be a part of.
It really is.
Always pushing the limits of what we can do with information.
But I'm curious, are there limits to what algorithms can do?
That's a great question.
Our source material hinted at something called complexity classes.
Ah, yes, complexity classes.
What are those all about?
They provide a way to categorize problems based on their inherent difficulty.
Okay.
One of the most famous and intriguing classifications is the P versus NP problem.
P versus NP. That sounds intense.
It's a big one. One of the biggest unsolved problems in computer science.
Wow, okay, so break it down for me.
In simple terms, P problems are those that can be solved relatively easily,
Okay.
meaning the time it takes to solve them doesn't grow outrageously as the input size increases.
Right.
NP problems, on the other hand,
Hmm.
are those where verifying a solution is easy, but finding the solution might take an incredibly long time,
Even for powerful computers.
even for the most powerful computers we have.
So P problems are the easy ones, and NP problems are the potentially hard ones.
That's a good way to think about it.
And the question is whether P equals NP.
Exactly. Is there a clever way to solve all NP problems efficiently?
And nobody knows the answer.
That's right. It's a mystery that has baffled computer scientists for decades.
It's fascinating and a bit humbling to think about.
It is. It really makes you appreciate the complexity of computation.
The idea that there might be entire classes of problems that are inherently difficult to solve.
It's mind-boggling,
Mhm.
but it also highlights the incredible ingenuity of algorithm design.
Always searching for more efficient solutions.
Exactly. Always pushing the boundaries.
This deep dive has been a real eye-opener. I'm amazed by the intricate ways in which algorithms shape our digital lives.
Me too. It's amazing to think about all the complex computations happening behind the scenes.
And I'm eager to hear what final insights you have to share with our listener as we wrap up this exploration.
Well, I think the key takeaway is that data structures and algorithms are fundamental to the way our world works.
Welcome back to the deep dive.
It's great to be back.
You know, it's amazing to think that these invisible forces are working tirelessly behind the scenes of our digital lives.
Right. It's mind-blowing when you really think about it.
And those invisible forces are algorithms.
Those elegant instruction sets we've been exploring.
Exactly. We left off talking about those incredibly clever algorithm design techniques.
Backtracking and dynamic programming.
Yeah, they really sound like secret weapons for tackling those really complex problems.
They certainly are powerful tools.
So let's start with backtracking.
Okay.
Remember that maze analogy?
Of course. Where you try a path, and if it leads to a dead end, you back up and try a different one.
Exactly.
It's a systematic way of exploring possible solutions.
Right.
If one path doesn't lead to the desired outcome, you backtrack to a previous decision point.
You go back and try a different route.
Exactly. And this technique is used in a surprising number of applications.
Like solving Sudoku puzzles.
That's a perfect example. You try placing a number, and if it doesn't work out, you have to go back and try a different one.
Uh-huh. Yeah, I've definitely experienced that backtracking feeling when I realize I've messed up.
We've all been there.
But it's not just Sudoku.
No, backtracking is also used in route planning, scheduling, and even in games like chess.
Wow.
The computer evaluates different moves and backtracks if a move leads to a bad position.
So it's really a versatile technique.
Incredibly versatile.
Now, what about dynamic programming? How's that different?
Well, while backtracking is about exploring all possible paths,
Okay.
dynamic programming is all about optimization.
Optimization.
It avoids redundant calculations by breaking down a problem into smaller, overlapping subproblems,
Right.
and then storing the solutions to those subproblems.
So you don't have to recalculate them every time.
That's right. It's like remembering the answers to a math problem you've already solved.
Right. It can save a lot of time and effort.
It really can. And this can dramatically improve the efficiency of algorithms, especially for problems where the same subproblems are encountered multiple times.
Like the Fibonacci sequence.
Exactly. Calculating the nth Fibonacci number can involve a lot of repeated calculations.
Right.
But with dynamic programming, we store the previously calculated Fibonacci numbers, making the process much faster.
And much more efficient.
Absolutely.
What other real-world applications benefit from this technique?
Dynamic programming is used in a wide variety of fields, actually.
Like,
One example is in bioinformatics, where it's used to align DNA sequences, which helps researchers understand the evolutionary relationships between different species.
wow, that's incredible.
It's also used in natural language processing, where it helps computers understand human language.
So it's really pushing the boundaries of what's possible in those fields.
It is. It's an exciting time to be working with algorithms.
This whole deep dive has been a real journey.
It has been quite an exploration.
From basic data structures to these complex algorithm design techniques, it's clear that these concepts are essential.
Absolutely essential to the way our digital world works.
So what's the key takeaway? What should our listeners be thinking about as they continue their journey into this world of data structures and algorithms?
I think the biggest takeaway is this.
Okay.
Data structures and algorithms are not just abstract concepts.
Right.
They're the foundation of everything we do with computers.
They're the building blocks of our digital world.
Exactly. And understanding these concepts, even at a basic level, can give you a new appreciation for how things work.
And maybe even inspire you to learn more.
Absolutely. There's always more to explore.
That's so true.
And for you listening, think about this. How can these concepts change the way you approach problem solving? Whether it's organizing your tasks or making decisions or simply appreciating the intricate systems that power our world, understanding data structures and algorithms can open up a whole new level of understanding.
It's like having a secret decoder ring for the digital age.
Exactly. It gives you a glimpse behind the curtain and helps you see the world in a new way.
Until next time, keep those brains buzzing and stay curious.
Stay curious.